Good day. Today we're going to look at basic probability. We're going to look solely on the tree diagram and the contingency table. We already discussed in class how we can look at the basic theories of probability. So this video is just to give you an activity or to bring everything into one place on how to plot the tree diagram and the contingency table. So here we have a question, and it's on width replacement. And the reason why we're looking at width replacement is because you're going to come across many questions that have this statement of solving probability question with replacement and with without replacement. So let's look at the question. Peter has a bag containing 4 green balls, 5 red balls in it. If he picks 2 balls at random, one after the other, but replaces each ball after selection. Draw a tree diagram to represent the situation. So we have 3 follow-up questions after plotting the tree diagram, which are: what is the probability of selecting 2 green balls? What is the probability of selecting at least one color of each? And what is the probability of selecting at least one color of red? Now, how do we go about this? First and foremost, we need to plot the tree diagram. Now, if you want to plot the tree diagram, it starts from a node. So we have the green and the red, right? And the next step is to we have the green and the red, and remember we are dealing with probability. And in total sample space, the total number of sample space we have is 9. We have 4 green and 5 red, which makes up 9. So we've put it in the fraction format here: 4 over 9 representing the green and 5 over 9 representing the red. Now remember, we are trying to plot a tree diagram, but this outcome is happening 2 times. So this is the first outcome. So in order to plot the second outcome, remember it's with replacement, selecting the ball. So you've selected the ball 4 out of 9, one ball, and the chance of selecting one green ball is 4 out of 9. Now, if the green ball is selected first, what if you select a green ball in the second outcome and then a red ball? And what if in the first outcome you select a red and now you select um, uh, a green and a red? So what will be the solution? Remember, we already have 4 over 9 in the green, and now the next outcome, because you are still replacing the ball, is still going to be 4 out of 9. What about the red? If you select green ball and then you select the red, 5 out of 9. What if you select a red ball and then you select a green ball? It is 4 out of 9. And the same thing for selecting a red and a red ball is 5 out of 9, 5 out of 9. So this exemplifies an example of a tree diagram. Now we are not done. The next step is that we want to complete the tree diagram by showing all the total outcome that we have. So we have 4 outcomes. The first one is a green and a green. Green, green. Remember, I used the word and. We also have a green and a red. We also have a red first and a green and a red and a red. So these are the possible outcome of selecting 2 balls, picking one after the other, and one is green and the other one is red. So what is the probability of selecting a green and a green? See, I used the word and remember, in our probability theory, if you go back to your notes, you will notice I said when you use the word and, you have to multiply. So for a green and a green, it is 4 over 9 multiplied by 4 over 9. And that will give you 16 divided by 81. What if you pick a green ball and a red ball? So you pick a green ball first and then you pick a red ball. Remember, with replacement, meaning when you select, you put the ball back into the bag. So it is 4 over 9 multiplied by 5 over 9. And I'm using the word and. Again, you select the red ball and the green ball, 5 over 9 multiplied by 4 over 9. And the last one is red ball and a red ball. You have 5 over 9 and 5 over 9. So right here you have all the fractions. And one way of confirming if your calculation is correct is to check all the denominators are 81. So if you add 16 plus 20 plus 20 plus 25, it should also give you 81. So 81 divided by 81 is 1. So this means our calculation seems to be correct, because probability, remember, always lies between 0 and 1. You can't have an answer greater than 1, neither can you have an answer less than 0. And this is a way of confirming if what you've done in your tree diagram is actually correct by summing up all the numerators, or simply summing up all the fractions, and if the total is equal to 1, then your answer is correct. Now that we are done plotting the tree diagram, we can proceed to with answer the question. Let's answer the question. Now the first question is the probability of selecting 2 green balls, and the answer is right there, 16 over 81. But you should remember the question is you're selecting a green ball and a green ball, and that is why you can just draw the answer simply from the tree diagram. This is why the tree diagram is very good in answering major probability questions. And okay, the second question, the probability of selecting at least one color of each. One color of each, meaning a green and a red, or a red and a green. You see, I use the word or in this sentence. That is, for me, the probability of selecting at least one color of each, a green and a red, or a red and a green. To select a green and a red, it is 21 over 81. Or to select a red and a green, it is 20 over 81. And then you divide and find the probability answer, you get 0.494. Okay, what about the third answer? Third question, the probability of selecting at least one color of red. This is one color of red, that is this. There's a red here, there's one red here, but there are two reds here. So it's these green, red plus red, green plus red, red. And then you have this answer of 0.802. Okay, and that is how you solve a probability question with replacement. Now, what if you're given a question of without replacement? Now we are looking at the same question, right? The same question with Peter having having a bag containing 4 green balls and 5 red balls in it, and the same question. But this time around, we are assuming that Peter selects the ball, but does not put it back into the bag. So how do you go about solving this? So I've done the first part of the selection for you. That is, we have the 4 over 9, the 5 over 9. Now let's complete the tree diagram. Now, the first part is if it's a green, and then you want to select a green. So assuming Peter selected a green first, it is 4 out of 9. Now, because it's not replacing the green in the bag, the denominator will reduce to 8. And the only possible event or you can select from, that is how many balls are left for Peter to select, how many green balls are left, is 3 out of 8. So does that have an effect on the red ball? Yes, it does. On the red ball, previously with replacement, it will be 5 over 9. But because a red ball was not selected first, but now it's selected the second time, so you still have 5 red balls. So each of the 5 red balls have equal chance of being selected. That is 5 divided by 8. What if you select a red ball first, 5 over 9, and now you're selecting a green ball. So if you select a red ball first, which is 5 over 9, selecting a green ball means that each green ball has an equal chance of being selected. But because you also didn't replace the red ball, the total denominator has reduced, or the sample space has reduced to 8. That's why it is 4 over 8. But what happens to the red ball? It reduces 4 over 8, because now you have selected a red ball, and now the number of other red ball will be 4, and because you're not replacing the total, the sample space also drops to 8. And if you look at the final outcome, this is what we're going to get. For the green ball, green, green, green and red, red and green, red and red. Slightly different from what we got with width replacement. So, question. Can you solve the probability of 2 green balls, at least one color of each and at least one red? I will wait for you to drop that in the comment section, or you'll just send me a reply. Thank you very much. Now in the next video, we're going to look at solving the contingency table.